Okay, so let's start. And so today we're going to learn a brandly new topic named dynamic programming. So let me first go through what we have learned. So until last lecture. So in the first 3 weeks, we spent the first, no, actually it's first 4 weeks, 3 or 4 weeks. I don't. Yes, let's say no. It's first 3 weeks on the topic of sorting. So that is our first chapter. So we learned literally we learned 4 different sorting algorithms, and then we spent another 3 weeks on the topic of basic data structures. So, and in this basic data structures, so this we learned in total, we learned 6 basic data structures. So which are the which are stack, queue, and the linked list. So the first 3 of them are mainly used for insertion and deletion because they provide so these 3 data structures are more efficient at insertion and deletion because they provide O1 complexity of that. After that, we learned that structure named binary search tree. So what is the point for us to use binary search tree, or what is binary search tree good at?
Going through and sorting nodes.
No. So it's basically no. The reason for us for people to design binary search tree is because of the search efficiency. So in binary search tree, so the other 3 data structures that we learned in the past 2 weeks, which are binary search tree, red-black tree, and then we also learned 1 data structure named hash table. So all of these 3 data structures are aiming for search because they are more efficient at a search. Whereas binary search tree provides OH search complexity, where H is the height of the tree, but H can be as bad as N, so it's not guaranteed to be efficient. And then we learned binary search tree, which guarantees O log N search complexity, and the hash table guarantees O1 search complexity. So these are the 6 data structures that we learned. So they have different purposes. So if you are dealing with a lot of insertions and deletions, you should consider one of these 3. Whereas if you are going to do a lot of searches, you should consider one of these 3: binary search tree, or red-black tree, or hash table. So this is what we have done. We have already learned in the first 6 weeks of our semester. In this semester, and then so next we're going to spend 2 weeks on topic named dynamic programming. So this is the most difficult one. This is the most difficult chapter throughout the semester. It really challenges your your intelligence. So from the coding side, dynamic programming is not that hard, but so it's extremely hard for you to understand it. So these 2 weeks are going to be rather tough for you. Okay. So, but the good thing is that after this 2 weeks, I'm going to give you a 1 week of rest. Okay. So we are going to have one week with nothing. So to help you to recover from this tough 2 weeks. So and then then we are going to spend 4 weeks on the last chapter. So and then we are going to have the final exam. Is this fine with you?
Yes.
Good.
Yeah.
Okay.
Yeah.
Okay. So, but actually, this 1 week of rest is not that much of rest, because I think most of you are going to spend that week doing the homework of the second homework of dynamic programming, and also digest the materials over here. And it's because really it's hard to understand it. When I was an undergraduate student, dynamic programming is when I took this course in my undergraduate years, for me, dynamic programming was like, did I ever learn that? So I didn't understand it, to be honest. And so hopefully I can make it a little better for you, a little bit better for you, and so you have so that you at least you understand what's that. But in these 2 weeks, I'm demanding a lot of workload from you guys, for you guys. Okay, so so what is dynamic programming? Dynamic programming is basically a general strategy to solve a computational problem, and it shares a lot of similarities with divide and conquer. So let me just show the difference, the similarity between divide and conquer and dynamic programming. So let's use the sorting as an example. Okay, in divide and conquer, let's think about the merge sort. What we do is that we first cut the big array into 2 halves, and we keep dividing them, and then we are going to focus on each of this individually, and then we combine the solutions together, right? This is how we apply divide and conquer to solve the sorting problem, and this algorithm is called merge sort. Do you still remember it?
Yes.
Okay.
Yes.
Yep.
Yeah.
Cool. So so the good thing about okay, and the good thing about divide and conquer is that when we divide the problem, say here when we cut this problem into 2 sub problems, those 2 sub problems, they do not overlap. Non-overlapping sub problems. Okay, so here you can see that these 2 arrays, they don't share any element. They're just totally disjoint with each other. Similar, when we cut this array into 2 halves, these 2 small subarrays, they do not have any overlap. And so we are able to solve each of them individually. Okay, so this is what we do in divide and conquer. But in dynamic programming, I'm going to use DP to stand for that, in short, for dynamic programming. Again, if we're giving a very large problem, so this problem may not be sort. It can be it can be a different problem. So the point is that, so when we use dynamic programming to solve a when we use dynamic programming philosophy to solve a very complicated, large and complicated problem, we also want to follow the strategy as what we do over here. We want to work on sub problems because they're easier for us to conquer. But the thing is here, say when we divide this big problem into sub problems, say we divide it in this way. So we divide it into the one that only shares the smallest one, which only covers the first element. for example, the first element of the input, and then we divide it into another problem whose size is 2, which is the sub-problem of size 2, and then size 3. And then we divide it into a we got a sub-problem of size 3, etc., etc. So we got all this. So basically, we're going to divide this big problem into multiple sub-problems, and then we're going to solve each of them. We will need to solve each of them. Okay, so we need to work on each of them. But the thing here is that if we look at the first 2 problems, they do overlap. So the second sub-problem overlaps with the first sub-problem over here. And then the third sub-problem overlaps with the second sub-problem in the first 2 elements. So here, what we do say is that in dynamic programming, even though we are cutting a big and complicated problem into sub-problems, these sub-problems do have overlapping sub-problems.
Professor, when you say overlapping, do you just mean the values of the like the elements?
Yes. So
okay.
It's like, so for example, if we take so if you remember in merge sort, I said that suppose that you are giving a very large car, you are asked to move a junk car to a junkyard by hand. So what we do is that in merge sort, if we use divide and conquer, the philosophy, what we do is that we move the wheels. Let's say we move the wheels, and then we move the say the engine. So we basically we're going to move each individual piece into the garage or junkyard, right? Okay, so that is what we do with divide and conquer. But if we use dynamic programming, dynamic programming over here, the things will be totally different. It's like, so it's like your mother is asking you to move, say, let's say the first third of the car to the garage, and then it asks you your grandmother is going to ask you to move, let's say the 2/3 of the car to the garage, and then the completed car to the garage. So over here you can say that every time when you're doing the moving, so they share something, right? So that is what I mean by overlapping.
Okay.
So that is that the sub problems, so there are some overlaps exist in the sub problems.
Okay, thank you.
Okay, so it may sound very abstract for you, but it will be a little bit clear after I present a very concrete example in a couple of minutes. So here as you can see that the biggest difference between divide and conquer and dynamic programming is whether there is an overlap in the sub problems that we divide. And this subtle difference actually has a big impact on the time performance of different algorithms. And okay, and so this is a brief introduction about the similarity and difference between divide and conquer and dynamic programming. So next, if you go through the book, actually the book spans around 15 or 20 pages. So discussing what is dynamic programming and what are the standard steps to solve a problem by using dynamic programming. And I'm just taking one summary, so summarize it over here. So if we want to use dynamic programming to solve a problem, so we need to follow 4 steps. So characterize the structure of the optimal solution and define the value of the optimal solution, and then compute the value of the optimal solution and construct the optimal solution. These are, I mean, like if there is no example for you, these sentences are like make a lot of sense. These sentences make so much sense that you even think that this is just a piece of garbage, because it's like saying nothing. We're not going to discuss these 4 steps in very details. So I want you guys to be practical. So here I just present one very concrete problem for you. Okay, so the very concrete problem is called rod cutting. So so the thing is that, okay, giving a rod of a certain length, okay, and also a table of prices. So then determine the maximum revenue that you can obtain by cutting the rod and selling it, for money. Okay, so this table just tells you, okay, if you sell a rod of length 1 inch, you will be able to get $1. If you sell a rod of length 2 inches, you'll be able to get $5. And if you sell a rod of length 3 inches, you'll be able to get $8, etc., etc. So this table just basically tells you the price of a rod of different lengths. Okay, and then what you are asked to do is this. Okay, suppose that you are giving a rod of this length, let's say of length 1, 2, 3, 4, 5, 6, 7 inches. You got a rod of length 7 inches. Okay, so what you are asked to do is that you are allowed to cut say this rod in any way that you want. And the ultimate objective for you is that, say, if you cut it into this, say, 3 pieces, 2 and 4 and 1. So basically, say you make 2 cuts, and then you got this rod into 3 different pieces, one of length 2 inches, and one of length 4 inches, and one of length 1 inch. Okay, and you sell each of them individually. So if you sell a rod of length 2 inches, how much money can you make?
5.
Yes, over here it says that you gain $5 for a rod of length 2 inches. You got $5. How much can you make from the middle part?
9.
Yes, 9, because it's 4 inches, and the price for a 4-inch rod is just $9. And how much can you make from the last part?
1.
1, yes. So okay, so the revenue that you can make from this cut is just 5 plus 9 plus 1 equals $15. Okay, so in this problem, what you are asked to do is to try to find the best way to cut a rod of certain length, so that when you sell those different pieces, and the total revenue that you can receive is going to be maximized. Okay, got it?
Yeah.
Okay, so this is our problem. Is there any question with regard to the definition of the rod cut problem? No? Okay, so then let me just make things try to make things a little bit easier for you. Okay, so next, let's say if we have a rod of length 1, how many ways do you have to cut it?
You can.
Just one way, right? If you got a length 1 inch, then you basically only got one way to sell it. Just got one way to sell it. You can only just sell it in a whole piece. From which you can make $1, correct?
Right.
Okay, and then if you have a rod of length 2 inches, okay, so how many ways do you have to cut it?
2.
So 2 ways. So the 2 ways are that either you cut it in the middle so that you get a 1 plus 1, or you just sell it in a whole so that you get say $5, right?
Right.
Okay, so then if you got a rod of length 3, how many ways do you have to cut it?
3.
3? Let's say
4.
4. Let's figure it out, okay, together. So one simplest one way is that you cut it into 3 different pieces, correct? So each of them is just 1 inch. Cut it inch. Okay.
Professor? Hello?
Yeah, I couldn't really hear you there, Professor.
Yeah.
Me either. You cut out.
How about now? Can you hear me?
Yes, we
Yeah.
can.
Yeah, now it's
Yep.
Okay. Cool.
Yeah.
So then the second way is that we cut into 1 inch and 2 inches, right?
Right.
Okay. And then the third way is that we cut it into 2 inches plus 1 inch. And the last way is that we don't cut it. We just sell it in 3. So as a whole, so in total we got 4 ways to cut it.
What about if you were to sell the first and last one? Would that make a difference, or I guess not?
Sell the first one and the last one.
No, like if you were to take the 3 that are totally separate, if you were
Uh-huh.
able to sell like the left and the right most one together, and then like the one in the middle would be like different. Or I guess that wouldn't. Never mind. That's dumb.
Okay, sorry, I don't quite catch your question, but here I just put 4 different ways to cut a rod of length 4. Okay, so then next, let's say if we are giving a rod of length 4, sorry, there are 4 ways to cut a rod of length 3, but say here if we're giving a rod of length 4 inches, how many ways are there for us to cut it? Yes. Can you guess how many ways?
Oh, I would just taking a guess. I guess 7.
7?
I'd say 5.
It's a guess. It's a guess.
Yeah, I think it's
7? Yes.
5.
5? Anything?
A lot.
A lot? Say how many? This is definitely countable. Within 20. It's a number within 20. Okay. So do you notice something interesting over here? So if we have a rod of length 1, we got 1 way. If we got a rod of length 2, we got 2 ways. If we got a rod of length 3, we got 4 ways.
8, 10.
So this one is twice as large as the previous one, and this one is also twice as large as the previous one. Right?
So the next one would be 8.
Yes. So the next one, the correct number over here should be 8. If we got a rod of length 4, there in total 8 ways. So basically, each time we just multiply the total number of ways by 2. And let's say what are these 8 ways? It's here. So we can sell this rod in a whole piece with 9. So we got $9, and then we can cut it into 1 and 3, 2 and 2, 3 and 1, 1, 1, 2, 1, 2, 1, 2, 1, 1, and 1, 1, 1, 1. So these are the 8 different ways for us to cut a rod of length, say 4. 8 different ways. Make sense?
Makes
Yeah.
sense.
Okay.
Yeah.
Cool. So then it will be 8 ways. And so let's say, okay, to be general, if we have a rod of length n inches, how many ways are there exist for us to cut it? Yes.
Would
How
it
many
be
ways?
t to the n?
Sorry? Can you say it again?
Well, isn't it just like exponents? So like 1 inch is like 2 to the 0, then 2 inches 2 to
Yes.
the 1. So it'd just be 2 to the n, or
No, 2 to the n minus 1. But
oh,
you're
n.
close.
Okay, yeah.
So when n equals 1, so this is 2 to the power of 0. 1 is 2 to 1. We only got one way. So 1 is 2 to the power of 0. So when n is 2, so we got number of ways as 2 to the power of 1. When n is 3, we got so we got 4 ways, which is 2 to the power of 2. When n is 4, it is 2 to the power of 3. So when we got n inches, so the number of ways for us to cut is just 2 to the power of n minus 1. Make sense?
Sure.
Okay. So okay, and okay, so then say if we are given such a problem, if we are given a rod of length n, what we can do is that we just enumerate one very intuitive solution is that we enumerate all the ways to cut it, and then from all the ways we just calculate how much money can we make from each way of cut, and then we get the solution with the maximum revenue. So basically, we want to try all the possible solutions and find the best one, right?
Yeah.
Okay, and then if we follow that way, there are in total 2 to the power of n minus 1 ways, right?
Right.
Okay, so this is 2 to the power of n minus 1 ways, and so then if we talk about the complexity, so we need to try all of these solutions and calculate their revenue. So in total, the complexity is going to be 2 to the power of n, because here when we're talking about complexity, we want to ignore we want to take off this constant over here. So the time complexity would be 2 to the power of n, or 2 to the power of n, if we want to enumerate all the possible solutions. Correct?
Yep.
Okay. So
Hey, Professor, for time complexity, I thought you dropped constants. So wouldn't it just be O to the n?
drop the constant.
Drop the constants. Like
okay, so you also want to drop off the 2 over here?
Well, I mean, just wouldn't we drop it off? Because I thought I saw something where you drop constants for time complexity. No.
Yes. Yes, we always drop constants from time complexity because the constants do not grow with respect to n.
Mm-hmm.
But here we cannot drop 2. If we drop 2, it becomes O(n). That will be totally different.
Okay.
Okay. So in computer science, if we got a solution with this complexity, we give it a name called NP hard. NP hard. NP stands for non-polynomial. Okay. So if NP hard or non-polynomial hard means extremely hard. So do you still remember last time when we talk about hash function, we say that it's going to be computationally impossible, infeasible to reverse a hash function. Do you still remember that?
Yeah.
Okay, so computationally infeasible is just, it has a term called NP hard. This is called computationally infeasible. Computationally infeasible. So to reverse a hash function, if we have a hash function that hashes any x to y, where y is let's say n bits, then the time complexity to reverse this function, to reverse this function is going to be to find the reverse of the function. Then the time complexity is going to be 2 to the power of n. So we call it NP hard or computationally infeasible to find the reverse of the to get the reverse of the hash function is NP hard or equivalently, which we call it computationally infeasible. Same here. If we want to enumerate other possible ways of calling a rod, and then the complexity is going to be NP hard or computationally infeasible. It's going to be computationally infeasible. Let's get a sense why it is computationally infeasible. So far, what is the highest complexity that we have learned besides 2 to the power of n? What is the highest complexity that we have learned? Let's say, okay, actually, that is n squared. So we learned n squared complexity from where? From insertion sort, right? The insertion sort algorithm comes with n squared complexity. So that's why when you're doing your homework tool, it takes quite some time for you to see the output, right?
Yep.
Okay, so this is n squared, and let's talk about 2 to the power of n, so which is the NP hard complexity that we learned today. So when n is let's say when n is 10, what is n squared? No, let's make it easier. When n is 1, what is n squared?
1.
1. And 2 to the power of n is 2. Okay, so if we increase n by 10 times, so when n becomes 100, 10, what is n squared?
100.
100. And what about 2 to the power of 10? It is 1024. Okay, when we increase this n to 100, so what is n squared?
1,000.
Sorry?
Or no.
10,000.
10,000. Yes, 10,000. And so what about this? What about 2 to the power of 100? So if 2 to the power of 10 is around 1,000, then 2 to the power of 100 is going to be roughly 1,000 over 2 to the power of 10. So it is like 10 to the power of 30. So just giving you a feeling. Okay, 1 billion is 10 to the power of 9, and 1 trillion is 10 to the power of 12. So this one, the number that we're getting over here is like a billion of a billion of a billion, 1,000 of a billion of a billion of a billion. Correct?
Yes.
So it's extremely large, and so that's why previously we say that when we learn hash function, we say that usually the number of bits for us to that we get from hash is 128 or 225, 256 or 251. So here n equals to either 128 or 256. So as you can see here, when n is 100, so the amount of efforts that we need to pay is already like 10 to the power of 30. Okay, so what does 10 to the power of 30 mean? So it means that we have to execute at least this amount of instructions on our computer in order to solve the problem. So what is the speed of your CPU? So here we say we need to execute this amount of instructions when in order to solve a problem, an NP hard problem when n is 100. Okay, so what is the, so we need this amount of instructions. So what is the speed of your computer?
It depends on the computer, doesn't it?
Yes. So for example, if you use an average i7 processor or i9 processor, it is around 3 GHz, correct?
Yes.
Correct.
So what does 3 GHz mean? 3 GHz means basically it means 3 billion instructions. It can execute up to 3 billion instructions per second. Okay, so this is the speed of a average computer. And if you use the most powerful computer in this world, it's around this. It is around 1000 GHz. Okay, so that, let's say that is around 10, so which can execute 10 to the power of 12 instructions per second. Okay, so if we calculate, so to solve the problem of size 100, we need this amount of instruction. And if you are giving the most powerful computer in this world, its speed is like this. So we can calculate the total amount of time that is needed to solve the problem. So we just need to use this number, 10 to the power of 30 divided by this number, that is 10 to the power of 12. So in total, we need 10 to the power of 18 seconds. 10 to the power of 18 seconds. So let me give you some rough estimate. Okay, so well, we have 1 hour. 1 hour equal to 3600 seconds, and then 1 day is like 12 hours, right? Sorry, 24 hours, correct?
Yeah.
So this is like 24 times 3600 seconds. So each day, let me say, is around so each day is around 100,000. Is roughly around 100,000 seconds. So each year, so if we multiply this number with 365, it's like the number of, so it's like the number of seconds that we have in a year. So it's like 33.6 10 to the power of 7 seconds. Okay, so this is roughly what the number of seconds that we got in 1 year. So if you use this number to divide this number, so we can say that to finish this calculation, so we will roughly need 10 to the power of 10 years. Even though you are giving the most powerful computer, which means that, okay, so you will need at least, let's say, 30 billion years to solve an NP hard problem whose input size is 100, and that is why we only need to require the number of bits in a hash function to be 128 or 256. So so if we use these numbers, it guarantees that it will take trillions of years for you to reverse this function. So whatever result you get from the hash function is going to be safe. And similarly over here, okay. So to find the best way to cut the rod of 100 inches, it will take us more than 30 billion years with the most powerful computer in this world. Now, I hope that after these calculations, you have a sense that this complexity, NP hard or 2 to the power of n complexity is really bad. It's really long. This complexity is the highest that you can expect on this world, in this world. Got it?
Yeah.
So any question for me before I continue? I know this sounds very mathematical, but dynamic programming has to be mathematical. That's why it's so hard to understand it. Any question for me with regard to the NP hard complexity or 2 to the power of n complexity?
Are there any benefits of dynamic programming, I guess? Or is it
Yes.
just-
Okay. Cool. So we got a very good question. Okay. Are there any benefits? Okay. So of dynamic program, if we do not use dynamic program, this is a non-DP solution, non-dynamic program solution, which is to enumerate all the possible ways and then calculate the best way. Then the complexity is going to be this 2 to the power of n. But in this problem, if we use dynamic program with DP, dynamic program, we can reduce the complexity from this NP hard to n square. Okay, so instead of, which means that instead of executing your program for more than 30 billion years, so you can finish the calculation with 10,000 say instructions, and just within 1 second of a normal computer. So now do you feel the power of dynamic programming?
Gotcha. Thank you.
Okay, dynamic programming reduces the execution time from this amount of years to 1 second. How powerful it is, right? Okay, so yes, and we're going to talk about dynamic programming. This is going to be our dynamic programming solution is going to be our focus in the Friday's class. And so I leave it for that one because I want to have at least 1 hour to go through that. And so and again, any question for me regarding the NP hard complexity?
Nope.
Yes or no?
No,
No questions.
No questions. Okay, cool. And okay, so okay, so this is the 8 solutions, or the 8 solutions for 8 different choices for us to cut a rod of length 4, and then so this is the mathematical solution, the mathematical solution for us to find the best way to cut a rod of length n. So what it says is that, okay, so Rn denotes here, Rn denotes the maximum revenue, that Rn denotes the maximum revenue that you can find, max revenue that you can find for a rod of length n. For an inch rod, okay? So here what it says that if you have a rod of length n, the maximum revenue that you can make is this. So Pn is the price of a rod of length n. So either say this is the solution, this is the solution of not cutting it at all. So just if you sell this rod directly, so which is n inches, then you will get Pn as your revenue. It's like no cut. Make sense?
Yeah, that makes sense.
Okay, and then so this is like cut. So we make the first cut at this place at the first place. So cut at the first place. So sorry, first cut at 1. So you make the first cut at this place, and then you are further allowed to cut. So it's like you make the first cut over here, and then you are allowed to further cut either the left or the right part. So for the left part, because you make the so its length is 1, so the maximum revenue that you can make from it is just R1. And for the right part, because you are making because you are you got a n-1 inches over here, so then the maximum revenue that you can get is Rn-1. So then you just plus them. Make sense?
Yep.
Okay. And then so basically this mathematical equation basically enumerates all the possible places of the first cut at I. So if we make the first cut at I, so then we got a I inch in the left rod, I inch rod on the left, and then we got n-I inch on the right side. And then the maximum revenue that we can get from the left hand side is Ri, and the maximum revenue that we can get from the right hand side is Rn-I. Correct?
Yeah, correct. But this would only work with the values that are already preset for the niches?
Yes.
Okay.
Yes. Okay. So basically, this mathematical equation is to enumerate all the possible i's. From 0, it will try all the possible places of the first cut. And from I equal to 0, meaning that no cut, to until from n-1. Okay, n-1 meaning that you make the first cut at the last possible place over here. So that you got a left hand side with n-I inch and the right hand side with 1 inch. So this is the mathematical solution for us to find the best cut. Okay, make sense?
Yep.
Okay, and then so this formula is really beautiful. So so here what it does is that because over here we got two revenues. So none of this is known. In the input we only know P, the price of a rod for a certain length, but we have no idea about R. So what this equation, so then those mathematical guys, mathematicians, they derive this formula. Okay, let me briefly explain that. Okay, so here they are just trying so if we're giving a rod of length n, so what it does is that they try the best place, try all the places to make the leftmost card. Okay, so here, if we make the leftmost card at this place at I, it means that we got an I inch rod on the left, and we've got a n-I inch rod on the right hand side. Correct?
Yeah.
Okay, but since this is the leftmost card, what we are not allowed, this part, the left part, is not allowed to be cut anymore. This is among all the possible cuts. This is the leftmost one. So whatever is to the left over here has to be sold in a whole piece. Okay, so how much money can we make from here, from selling a rod of length I without any cut? It's basically PI. P is the input array. So PI stands for the money that you can make from selling a rod of length I inches without cutting it. Okay, so this is PI because we're not allowed to cut the left part anymore. So we just sell it directly. If we sell it directly, this is the amount of money that we can make. Make sense?
Makes sense.
Yeah.
Okay, but for the right part, we are allowed to cut it as many times as we want. We are allowed to cut it as many times as we want. So the maximum revenue that we can make from the right part is Rn minus I. Here, Rn. Here, remember, Rn stands for the maximum revenue that you can sell. You can make from selling a rod of length n. So because here we have N minus I, a rod of N minus I inches, and we're allowed to cut it as many times as we want. So the maximum revenue that we can make from it is just Rn minus I. Correct?
Yeah.
Okay. So then the total money that you can make from making a leftmost card at the ith place is basically PI plus Rn minus I. Correct?
Yep.
Okay. So what it does is that, okay, to try all the possible places of the leftmost card, where I starts from 1 until n. So it try all the possible places of the leftmost cut, and then so calculate, okay, the revenue from each possible places of the leftmost cut, and then return you from all these possible places of the leftmost card. It will return you whichever gives you the maximum total revenue.
Wait, can you say that one more time?
Okay. So what this does is that what this equation does is that if we're given a rod of length I, so it will try to say, okay, let's make the first cut at 1, and then let's try to make let's try another choice of making the first cut at 2, and then at 3, and at 4, etc., and then it will calculate the highest revenue, the revenue that you can make from all these possible places of the first cut. For this one, the revenue that you can make is P1 plus Rn minus 1, correct?
Yeah.
Okay. For this one, what you can make is P2 plus Rn minus 2, etc., etc. It will try all these possible places and say, okay, whichever gives you the highest revenue, it will take the place that gives you the highest total revenue. Make sense?
Yes.
Okay. So let me say, how do I give an example to explain that? Okay. So okay, so okay, let's put it in this way. Suppose that you have a big house with 5 rooms. So you want to find the best way to rent these rooms in order to make you the most amount of money. Okay, so what you can try is that you try to rent it in 1 and 4, meaning that you rent this room to a single person and rent these 4 rooms to a family to say how much money can you make in total. And then you try another way of, let's say, you rent it out with 2 rooms plus 3 rooms, and then 3 rooms plus 2 rooms. So basically, you try all the possible ways of renting out this room and say whichever gives you the highest amount of revenue. This is pretty much similar as what we do over here. We try all the possible places of the leftmost cut and find whichever gives us the highest total revenue. Make sense?
Yeah, that was a good example.
Okay, thank you. So then this is what the math guys are doing. And so let me say, okay, let me make a stop over here for today and leave the rest for Friday. I think it's already too much. I don't want you guys to be bored by me. So I'm going to be slow with dynamical programming, and because it involves a lot of math, and we will restart. So until in this lecture, so I know a lot of things seem very, very abstract for you, but the two things that I want you to digest is the exponential complexity, or NP-hard complexity. Means that it's really hard. So hopefully that you can feel the difference of like 3 billion years, and then and the other thing is this mathematical formula. Okay, so just try to understand this mathematical formula, and on Friday we will start from here. Okay, so if you have difficulty with understanding my lecture for today, please go to this subchapter 15.1 to read it. So this is the first time that I require everybody to read a chapter, a subchapter. It's really important. If you only come to my lectures without reading the book, to be honest, I'm not sure. I'm not confident that I can explain everything very well to you, because it's very mathematical. So I would like you to, I require you to spend some time reading the textbook. This is the first time I make this requirement in this course. So take it seriously. Okay, so any question for me?
Can I speak to you afterwards in private? I don't know if you got my message in the chat.
Sure. So no problem. Well, we can talk after this. Okay. Any other question for me?
Yeah. I have a question about the complexity thing.
Okay, sure.
So I don't really understand how the complexity is 2 to the n, and how that's NP hard.
Okay,
but
so
is 2 to the n the complexity of dynamic programming?
no.
Okay, all right, yeah, that's where I was getting confused.
Is the complexity without dynamic programming. If we just try the most basic way, which is to enumerate all the possible solutions, then the complexity is going to be 2 to the power of n, which is NP hard. But with dynamic programming, we can reduce the complexity to n squared.
Oh, okay, all right. Yeah, that all right. Thank you.
No problem. Any other question for me? Okay, so then if no question, then that's it for today. Oh, by the way, thank you for making your comments on the website. I saw it over the weekend. Thank you very much. And yeah, same to you.
I'm sorry. Have a good day, though.
Yo, thank you. So we'll continue this topic this Friday. Take care.
Thank you. Bye.
Thank you.
Have a good day. Bye-bye.
You too.
Take care. Thank you.
So is there anyone who have individual question for me?
I don't know what the others are doing here, but I know I definitely want to speak. With
Okay,
you.
so you want a private call, right?
Yeah, I mean, I
Okay.
don't know if others
Sure.
have questions.
Let me
maybe
do
they'll
this.
go
Okay,
first.
let me end this meeting now, and then I'm going to start this meeting again. So just
Sure.
just join this. Just join this meeting. Just like wait a couple 5 seconds and join this meeting again. So
Sure.
so
that'll be
then
fine.
we will be two of us.
All right. I'll see you in 2 seconds.
Thank you.